Okay, so I'm going to do a brief review of lesson 17. I think the Apple Pen has died, so it's good that these are all filled in because this was the first lesson we did for this next test, and I'm not going to go back and record a full video because I actually wrote the notes out and tried to make my handwriting really nice. And so to start off with lesson 17, we talked about acid-base classification. One of the first things we said was that a proton and a hydronium ion are, they mean the same thing. The only difference between them is a water molecule. And so sometimes we're kind of lazy and we just write in the form of a proton. But most of the time we're talking about a hydronium ion. And the OH is the hydroxide anion that's going to be present in these aqueous solutions. So the first model definition we had was the Arrhenius acid and base. And these acids will increase the concentration of protons in solution, so they must have a proton in their formula that's available to be dissociated, whereas the bases are going to increase the concentration of the OH. But the problem is that not all acids and not all bases have a proton or have a hydroxide, but yet they are acids and they are bases, and we know that because we measured their pH and we can see that. So the most obvious example is ammonia, which I hope you guys remember as being the most weak base, or most common weak base that we see. It does not have an OH available, so it's not very clear that it is a weak base, but yet it is. Its pH is something we can measure as being basic. Now the Bronsted-Lowry model helps to take into account the problem with the Arrhenius acid definition, acid-base definition. And that's that Bronsted-Lowry acids and bases are going to be defined on how they accept or donate protons specifically. So it does not require an aqueous solution, which helps address whether or not they have a proton or a hydroxide. So Bronsted-Lowry acid is going to be something that is a proton donor, whereas the base is going to be the proton acceptor. So if we think back to ammonia and its structure, it's NH3, its trigonal pyramid, has that lone pair on the apex of the nitrogen, which is where the proton, which is electron deficient, we know that because it has a positive charge, indicating it's has less electrons than what it would like. So therefore the nitrogen is going to donate both of its both of its electrons in the lone pair to form a covalent bond with hydrogen, and that forms the cation we know as ammonium ion. And that's what makes ammonia a weak base, its ability to accept that proton. So now in problem 3, we have an example. We want to categorize them as either being an acid or a base. And so if we're looking at it, we have acetic acid, CH3COOH, plus water to form the acetate ion and hydronium. So because acetic acid is giving up that proton at the end of its formula, we know it's giving it up because from left to right, the only thing that's changing is the loss of a hydrogen and a positive charge, which indicates the loss of a proton. So that makes acetic acid my acid. Now water in this case is what's accepting the proton, because from left to right what's changing is it's going from H2O to H3O plus. So it's gaining that hydrogen and that plus charge, which is what makes hydrogen, which is what makes water the base in this case. Now if we reverse the reaction, so took our products and moved them over to the reactant sides and took the reactants and put them on products, we see that they switch. The acetate, which was formed from an acid, is now going to be defined as the base, and the water, the hydronium, which was formed from the water, which was our base, the hydronium is now considered to be the acid. And so we see the relationship switches from left to right. If something is an acid on one side, it forms a base. If something is a base on one side, it forms an acid. Now, we call these pairs conjugate acid-base pairs because they occur together, so they're going to be pairs on left and right, not pairs on the same side, but pairs on the opposite side. So when you have a balanced chemical equation for acid-base, you're going to have an acid and base present on both sides. One on the left, one on the right of an acid, one base on the left, one base on the right. So when an acid reacts and loses its proton, like acetic acid, it forms a conjugate base. Again, that reversing of the reaction above is what makes it a base, because if we reverse the reaction, it's now accepting a proton to form acetic acid again. Now, ammonia, on the other hand, when we talked about ammonia accepting a proton and defining it as a base, it formed ammonium ion, which we can now define as a conjugate acid. So we then predicted the products based on whether or not it was an acid or a base. So HNO3, nitric acid, is a strong acid, one of our 6. Therefore, it's going to donate a proton. We're not going to change the behavior of nitric acid to make it behave as a base. We're going to accept the fact that it is an acid, and that's how it's going to behave. Because it gives up its proton, it gives up the hydrogen and the plus charge, which forms NO3-, which was our nitrate ion. So remember, ates become ics, ites become us when we name our acids. And so NO3- nitrate is the conjugate base. Now phosphate, on the other hand, has no protons to give up, so therefore it has to be behave in a base form. The negative charge suggests that as well. It's going to want to accept a proton to get rid of that negative charge, the 3-. But we also see there's no protons for it to give up. So when it accepts a proton, it accepts the H and the plus, meaning the conjugate acid that forms is HPO4 2-, because it's going to add a hydrogen and it's going to add that 1+, which makes it less negative. Now, CH3NH2 is identical to ammonia, except for instead of having a third hydrogen group, it has a CH3 group. And I admit this is a little bit more complicated than what I would probably give you, because this is an organic molecule, meaning there's not a single center atom. You know, this might be something you might see in organic and not necessarily on a Gen Chem test. But it is similar to ammonia. I do want you to be able to see that. So I drew the structure out here. Because it's identical to ammonia, it's going to behave as a base, meaning it's going to accept a proton with that apex lone pair at the top. And it's going to form CH3NH3 with a plus charge. And that's still a conjugate acid, just like ammonium was. Now, HCO3- can behave either way. It can either accept a proton to get rid of that minus charge and add an H, or it could lose the H it already has and become a CO3 2-. So when we lose the hydrogen proton, it forms CO3 2-, which is a conjugate base because it's formed from an acid. Now, if I want to add a hydrogen, I form H2CO3, which is carbonic acid, and now it's conjugate acid because it's formed from a base. Now, water is unique because, for several reasons, but one of the things that makes it unique is the fact that we classify it as a universal solvent. A universal solvent means most things dissolve in it, and that's true because water can act as an acid or a base. It's not limited on that particular property. So any compounds that have this ability, we call them amphoteric, kind of like ambidextrous means you can write with both hands. Amphoteric is kind of the same thing. You can give up a proton or you can gain a proton. And so in this case, we labeled hydrofluoric acid plus water. We labeled acids and bases, conjugates on both sides. And so it's important to note here, conjugates are on the product side, acids and bases are on the reactant side. So the conjugates are formed. The acids and bases are what we're reacting. So make sure you're not defining reactants as conjugates, only products. So with hydrofluoric acid, water is going to act as a base, and with ammonia, water is going to act as an acid. Just based on what it's present with, it can accommodate the other species. Now, then we started getting into some of the formulas that we have been using all through chapter 14 and some of 15, based on this property of water called autoionization, meaning it automatically ionizes with itself. It doesn't need any sort of external work or energy to do that. And so we wrote the autoionization equation where one of them's giving up a proton, one of them's gaining a proton. So one is acting as an acid and one is acting as a base. And then we wrote an equilibrium expression with our formula from that autoionization. The waters on the bottom cancel out because it's a liquid. It's going to equal 1. And that leaves us with this important formula called Kw equals hydronium times OH, which is the equilibrium constant of water, which is 1.0 times 10 to the negative 14th, only at a temperature of 25 degrees Celsius. So that is a standardized number. If you're at a different temperature, oddly enough, this value is not going to be equal to 1.0 times 10 to the negative 14th. It is influenced by temperature. So then it says, using the value of Kw, calculate hydronium and hydroxide at equilibrium. Well, this would mean that the concentrations of both of them must be equal. We call that a pH of 7. And so we're going to plug in x's for our concentrations because we don't know those values. We have Kw. That gave us x squared is equal to Kw. We took the square root of both sides and got 1.0 times 10 to the negative 7th. So when the concentration of H plus or OH minus changes in solution, the other one must change according to the constant Kw. So if hydronium is going up, hydroxide is going down. It's kind of like a seesaw. If hydronium is going up, that means the pH is more acidic because it's present in the majority. And OH is less, meaning there are still some basic components in solution, but the predominant species is an acidic species. And so then we did a problem with the strong acid because HCl fully dissociates into H plus and chloride. All of the protons that contribute to the pH are going to come from HCl. And so we're going to plug that into Kw and solve for the OH concentration, which gave us 2.13 times 10 to the negative 13th molar. So we can see there's way more hydronium ions present than hydroxide. And therefore it's going to be a strongly acidic solution, not basic. Anderson, you're just going to have to set this in here. Okay, just like that. Just be easy. I'm playing with Play-Doh. Okay, so then I gave you two formulas here. pH is equal to the negative log of hydronium, remembering that hydronium and proton are equal to each other. Therefore, they're interchangeable. We don't have to have a different one. And then if we wanted to reverse the equation and solve for hydronium, you use the one at problem 9. Just a reminder that the pH scale runs from 0 to 14, with 0 to 7 being acidic, 7 to 14 being basic. Only 7.00 is considered neutral. So just to remind y'all, remember I told you we typically report our pH numbers to 2 decimal places. Okay. I noticed that a little bit on the quiz that we had some that were giving several decimal places, like 8. And then I had some of you that were just rounding up. And it's going to be important because on the test I have to put in a range of numbers that I'll accept. And I'm going to run that range of numbers based on the hundredths place, not the tenths, and certainly not the first place where, you know, if the pH is 7.5 and you put 7 or you put 8, it's going to be wrong. If the pH is 7.52 and you put 7.5, it's still going to be wrong because the pH is 7.52. It's somewhere between 7.19 and 7.24. Okay, so I have to put in ranges, and so you need to make sure you're reporting your decimal places. And I think I got those numbers mixed up. I should have written that down before I said it out loud. The important thing is just make sure you put the decimal places to 2 when you're reporting pH or pOH. All right. Then we have this important relationship that we've used quite a bit, which is pH plus pOH equals 14. So if I have pOH, I can solve for pH very easily using this formula. Then we practiced 3 problems of how to calculate the pH. And so this is the part where we tend to make a mistake, specifically on B. You're given an OH concentration, something that's basic. And when you're solving for pOH, when you're using hydroxide, you're not solving for pH, you're solving for pOH. And so that was another mistake on the quiz, especially the buffers. You guys were solving for pOH and then not going back and converting that to pH. So You always need to be mindful, do I have something that's basic and I'm expected to report acidic, or is this acidic and I need basic? But make sure you're reading carefully, because in this case, and on the quiz, the final answer, I expected it to be in pH, which means you had to subtract your answer POH from 14 to get the right answer. Okay, so hopefully this will help. Just a quick review of lesson 17. I'm going to post a practice exam and do a short video kind of similar. Since the pen is dead, I'm not sure how I'm going to do this, but I'm going to try my best to do that, set up a video today, so you'll have something going forward for the test on Monday.